Okay, now that we've built up some intuition for random variables, let's look at the continuous case. So what if we had a random variable and we decided we wanted a range consisting of one or more intervals of the real numbers? So for instance, let's measure a voltage, and the number that we might get might be between -5 and +5 volts, but we might not expect a discrete set of values, but rather anything along that continuum. So maybe -1.3782, so on. Range is no longer discrete in this case, and so we need to define a new kind of random variable to deal with this situation, which shows up all the time in engineering models. So let's just say we have a wheel of fortune and it has diameter exactly 1 meter. So what we're going to do is we're going to spin this wheel very fast and record where it stops. And this stopping position we're going to say is between 0 and 1. And since we spun the wheel so fast, it's reasonable to assume that every stopping position is equally likely. Okay, and so what we're going to do is model the kind of random variable we get from this and trace this all the way through so we understand how continuous random variables work in terms of their foundations. And then after that, we're going to switch to doing some more examples. So for the first part of this video, you just kind of need to get the idea. You don't need to follow all the calculations exactly. And then later we'll shift to doing some longer examples. So what we have is a random variable, and we'll call it x, and we'll say it's equally likely to take any value in the unit interval between 0 and 1. What's the probability that it takes a specific value? So like, let's say I'm wondering if it takes a value exactly 0.50000000. Intuitively, this should be 0 because it's extremely unlikely that I get exactly the decimal representation that I picked. It makes sense that there's a probability that lies between 0.5 and 0.57, but not to be exactly at 0.5 with infinite zeros afterwards. And so what I want to do is use my knowledge from discrete random variables to model this scenario and see what's going on. The way I'm going to do that is instead of working with the continuum, I'm going to divide the wheel into n pieces of equal size, and I'm going to let y be the slice I land in. So formally, y is a function, which is the floor of n times x divided by n. And what that means is that I get these values 0, 1 over n, up to n minus 1 over n. So that's like a quantization or discretization of my continuous random variable. What it looks like is at 2, I have 2 slices. At 4, I have 4 pieces. 8 pieces, and I'm just going to keep going as I take the limit to infinity. I'm going to get the following PMFs. So I'm going to half and half because I'm equally likely to land anywhere. So I'm equally likely to land in blue or in red. Then when I go to 4 pieces, I get 4 pieces with 1/4 each, then an eighth each for 8. And you can see that these values have to go down to 0 as n goes to infinity. And so what that means is this PMF actually kind of becomes useless for us because all we can say is that there's a bunch of 0 values. We can't actually calculate anything. So what happens to the CDF? Well, the CDF is the probability that I'm less than or equal to a value. So it goes up in these jumps of 1/2, then these jumps of 1/4, and then these jumps of 1/8. And what's interesting is if you keep track of these jumps, eventually you'll see that you just end up getting this slope 1 curve from 0 to 1. And so I get a function that makes sense even as n is going to infinity, whereas the PMF stops making sense. Okay, so this is the problem with continuous random variables. Even if we want to define a PMF, it's just going to say 0 everywhere, but the CDF is going to be well behaved. Okay, so specifically in that example, as n goes to infinity, we saw we got the following CDF. It was y from 0 to 1, so it went up with slope 1, and started at 0 and ended at 1. It would be nice to have a visual way of seeing the fact that the positions on the wheel between 0 and 1 are equally likely. And it turns out one way we can do this is to just take the derivative of the CDF. So if we take the derivative of this function, we'll see that it's 1 between 0 and 1 and 0 otherwise. And so I get this nice flat function between 0 and 1. And that flatness captures the fact that any position between 0 and 1 is equally likely. And remember that this is not actually the probability. When we take the derivative, it's not telling us the probability that I'm equal to a specific value because that's always 0. Okay? It's going to tell us something slightly different. We'll see what that means in a little bit. Okay, so this derivative is just a representation that the positions are equally likely, but it's not really telling us the probability directly. What is telling us the probability directly is this CDF, or cumulative distribution function. So remember, we defined this a little while ago, and we said that the cumulative distribution function, or CDF, written as capital F of x, that is the probability that a random variable is less than or equal to a value little x. Okay, so formally, it's the probability of the outcomes in the sample space that get mapped to little x or less. And we write that in shorthand, just dropping all of the sample space stuff. And often we just write as probability that random variable is less than or equal to x. And that's probably the most convenient. The key thing to remember is that we have this idea of continuity. So a CDF is continuous if it doesn't change abruptly. Formally, that's that its limit, as you take this epsilon push down to 0 around any point x, that doesn't change the function. So as an example, here's a discontinuous CDF. So here, if I move a little bit off a point, I could jump by a lot. So that's something that we see. Whereas here I have a continuous CDF. If I push by a little bit, I just kind of maintain the same kind of value. And that's something that we're used to seeing in the discrete case, but in the continuous case, we're going to insist that a random variable has a continuous CDF. So if you're going to be a continuous random variable, you need a continuous CDF, and you need that CDF to have a derivative. So it needs to be differentiable almost everywhere. Now, this is kind of a technical term. What it means is that it's okay if there are a few spots where you don't have a derivative. Okay, and this seems very technical. And fortunately or unfortunately, we've already run into that scenario. And so let's see what it means. So remember that a derivative exists at a point x if we can take a certain limit and show that that limit exists. So if I have the function evaluated at x plus epsilon and at x, and I take the difference and I divide that difference by epsilon, and I take the limit as epsilon goes to 0, if that limit exists, then that's the derivative. Okay, so let's look at the function that we just defined. So it was slope 1 between 0 and 1 and flat otherwise. Here's what it looks like. So where does the derivative exist? Well, it exists at this 1/2 point, but it doesn't exist at this 0 point. Let's see why that is formally. Well, if I take the limit as epsilon goes down at the 1/2 point and I approach from the right, the slope is always 1. So this limit will also be 1. If I take this slope from the left, I'm also going to see that it's 1. And so this equation works out to 1. And so the limits from the right and left are equal, so the limit or the derivative exists. But what if I look at this point at 0? So you can see the same thing's not going to work. If I come from the right, the slope is always 1. And I can work out that as epsilon goes down, I get 1. But if I come from the left, the slope is always 0. And if I plug in those values as epsilon goes up to 0, we can get 0. And so these don't agree. And that means the derivative technically doesn't exist. But that is totally fine. We don't need to worry about that in this setting. So all we need to worry about is that there's just a few of these points, or a countable number of points where that happens. And we can just put any value that we like there. So what we're going to end up with is this probability density function. And this probability density function is going to be the PDF written as little f of a continuous random variable x. And all it is the derivative of the CDF, big F. Okay, so I just take the derivative of the CDF where the derivative exists, and where it doesn't exist, we just don't worry about it, and you can put any value that you like. We'll just pick something convenient. So as an example, we come back to this function that we had. When I take the derivative here, there were a couple of points where the derivative doesn't exist. I don't even worry about them. I just write the derivative as this box from 0 to 1. Okay, and here I can write, just to show you, here's another kind of derivative I could get. So I kind of have this derivative that's increasing and then decreasing as the function slows down. And the one thing to keep in mind here on this plot is that even though the CDFs are always bound to be less than or equal to 1, because probability is less than or equal to 1, you'll notice that this right PDF actually went above 1, and that is totally fine. It is okay for it to exceed 1, because this is not a probability, it is a density of probability, and it's okay for density to exceed 1, probability can't exceed 1 itself, but its density can. Okay, so what this PDF function little f is doing is it's not telling us the probability that x is equal to a value little x. That is always 0 for a continuous random variable. Okay, we just always know that's 0. What it's telling us is the density of probability around that point x. Okay, so this idea of density is going to be really important. And so what we can do is if we can use this density function to say if we want to know the probability in a little interval, let's say it's from a to a plus delta, the way I can do that is I can work out what the function is at a and just multiply by the width. Okay, and then that's a pretty good approximation. So this delta times f at a is a pretty good approximation of the probability that x lands in that interval. And as delta goes down, that approximation gets better and better. And that turns out to be basically integration. Okay, so let's make it integration. That's going to be the exact value. So the exact value of the probability that I land between a and a plus delta is just the area under the curve defined by this PDF. Okay, so if I want to know this probability that I land in the interval, what I should do is integrate the PDF. That's it. So intuitively, the main thing that we should take away from all the stuff we did before is that the PMF is gone, but we can basically recover everything that we want using the PDF as long as we replace sums with integrals. And we remember that we can't just plug in a specific value to the PDF and expect to get a probability. That's always going to be 0. But the main thing to keep in mind is just replace every sum with an integral, and now we have a nice equivalent for the PMF. Let's look at some of its properties. So let's do it for both the PDF and CDF. Okay, so on the left we'll have the PDF, and on the right we'll have the CDF. So non-negativity for the PDF translates to it being non-negative, and for the CDF it translates to non-decreasing. Normalization means the integral across the whole range from -infinity to infinity is going to be 1, whereas for the CDF it means at plus infinity I'm 1, and I start at 0. I can translate between PDF and CDF by taking derivatives to go from the CDF to the PDF, wherever it exists, and where it doesn't exist, I just put whatever value I like. Again, don't worry about that. To go from the PDF to the CDF, I just do the opposite. I integrate up to the value I care about, right? So if I'm interested in figuring out the CDF at a value x, well, the CDF is just the probability that I'm less than or equal to x, so I integrate all the way up to x. And I don't want the x to show up in both the limit and as the integration variable. So here I'm using u as a placeholder integration variable so I don't get confused. Finally, if I want to know the probability that I fall into an interval, if I use the PDF, the probability I fall between a and b is the integral from a to b. And for the CDF, it's the difference in CDF values, starting from b, subtracting a. And the nice thing about continuous random variables is since the probability of a specific value is equal to 0, there's no distinction between the probabilities of open and closed intervals. So you can have strict inequalities or non-strict inequalities, and that's going to be fine. You can just calculate them in exactly the same way by integrating from a to b. Finally, with all of this background in mind, we're going to work out some examples, and I think that'll make things more clear. So as an example, let's say I have this random variable x. I tell you it's equally likely to take any value in the interval from half to 3/4, and I want to figure out what its PDF should be. Right? And it's easier to start with a plot. So we know it's equally likely, so we want to have a plot that's going to be flat between half and 3/4. So that's all I'm going to do. I'm going to draw this flat region here. Okay, and it's going to have a certain height. And I need the total area to be 1 to satisfy normalization. So I'm going to set the height so that the area is 1. So the area is 4 times 3/4 minus 1/2, which is 1. So that's why I picked 4, because the length of this box was 1/4. So 4 times 1/4 is 1. So overall, case by case, I could write this as a PDF that's going to be 0, less than 1/2, and then it's going to be 4 between half and 3/4. And then it's going to go back up, or sorry, back down to 0 after 3/4. What's the CDF going to be? Well, two ways we can do this. I can either guess the integral just by looking at the plot, or I can compute it directly. And we're going to try both methods. Okay, so looking at the plot, I see that the plot is actually a plot of the slope of the CDF. So the slope is 0 for a while. So I just stay at 0, and then I start going up by slope 4 until I hit 1, and then I stay flat again because the slope is 0 again. So this is where the slope is 4 as predicted by the PDF. Or I can compute it directly. So I had that formula which said I can integrate the PDF to get the CDF. So I'm going to do that. So integrate up to this value x using u as my integration variable. And frankly, at this point, it's going to get a little bit annoying and tedious, but we're going to follow this through just so we see the mechanics of it. So I'm going to get an integral which is integrating 0 for a while, because when x is less than 1/2 and I plug into the PDF, I just get 0. So for a while, I'm just integrating 0. Once I cross 1/2, then I'm going to be integrating something more interesting, which is 4. Okay, so between 1/2 and 3/4, I get this integral, which is I have to break up into these two parts. So there's a part where it's 0 up to 1/2, and there's a part where it's interesting and I'm integrating 4 from 1/2 up to x, if I know x lands between 1/2 and 3/4. After that, after I've crossed 3/4, I'm going to be integrating 0 for a while, and then 4 for a while, and then back down to 0 for a while. And I can complete all these integrals, okay? And if I work all of them out, what I'm going to find is there's going to be 0, okay? And this next one is going to be 4x minus 2. And finally, this last one is going to be 1. And you can work all of these out carefully, or for the first and the last one, you can just keep in mind that the CDF has to start at 0 until something interesting happens in the PDF. And then after all that stuff has passed, it has to settle into the value 1. So the first and last values I could have just plugged in, knowing those two facts. Okay, well, let's stay in the same example and let's actually try to figure out the probability that I land between 1/2 and 7/12. Okay, so in the PDF, to calculate the probability, I work out the area under the curve. Okay, so here's 7/12, and I'm going to calculate this area under the curve. That's going to be my probability. All right, so probability for this PDF is the area under the curve. So I'm going to integrate that from 1/2 to 7/12. I'm integrating the PDF, and I plug in, and I know that in that region, it's going to be 4 for the PDF. So I plug in 4 dx, and I get 4x evaluated from 1/2 to 7/12. And so I plug in, it's 4 times 7/12 minus 1/2. That's going to be 4 times 1/12, which is just 1/3. How do I do the same thing in the CDF? Well, if I want to calculate it in the CDF, it's just going to be the difference in heights. Okay, so CDF probabilities, I take differences in heights, and it's going to be, in this case, 1/3, the difference in heights. And let's see that from the equation. So if I work out what the values are going to be at these 2 points, I'm going to also get this formally. So I get the CDF at 7/12 minus the CDF at 1/2. Plugging in, I would get 4 times 7/12 minus 2, because you remember we had 4x minus 2 for the CDF in that region. And then I can plug in again, 4 times 1/2 minus 2. So I get 7/3 minus 2 is 1/3. Okay, so they give the same answer, just different ways of calculating the same thing. Use whichever is more convenient. Okay, and now I want to show you one pitfall you could run into. So let's say we just try another probability calculation. What's the probability we fall between 5/8 and 1? Okay, again, it's going to be the area under the curve. Okay, I'm going to try to calculate this using the PDF integral. So I integrate from 5/8 to 1, and I have the PDF, and I'm going to start plugging in. So far, everything I've done is actually correct. I'm going to see what might go wrong here. So I'm going to plug in the value of the PDF, which I know is going to be 4, and then I end up going 4, which is 1 minus times 1 minus 5/8, and that's going to be 12/8. And this is greater than 1, which obviously can't happen because probability cannot be greater than 1. So what went wrong here is when I plugged in to work out this integral, this actually turned out to be wrong, okay, because I was a bit careless. What I should have done is broken this into 2 parts. There's a part going before 3/4, where the PDF is actually taking value 4. And then after 3/4, it's taking the value 0. So between 3/4 and 1, I should have plugged in 0. And I've correctly now split this into 2 cases. And so what I would get here is 4 times 3/4 minus 5/8, which is just 1/2. Okay, so visually, what I need to do is remember I'm taking the area under the curve, and then the area under the curve between 3/4 and 1 is 0. And if I just carelessly plug in to the formula and I don't pay attention to the cases where that's valid, I could make an error. Okay, so it's important, sometimes it's helpful to look at the plot to know where I should change the evaluation. In the CDF, we don't run into the same problem. Okay, so calculations are a bit different. I just take the difference in heights. So I have CDF at 1 minus CDF at 5/8. It's 1 minus 4 times 5/8 minus 2. So that's 1 minus 5/2 plus 2, and that's 1/2. Okay, so it's just the difference in heights. Okay, so why don't I have to worry about that? Well, it turns out the reason I don't have to worry about it in the CDF is that I've actually already worried about it. So when I calculated the CDF, okay, so on the previous couple of slides, I've been working out the PDF and the CDF. I had to be really careful when I worked out the CDF because there were lots of case-by-case integrals involved. And if I did those correctly, then all of the little nuances with the integration regions are already handled, and I'm free to just plug into the CDF. Whereas what I'm really doing here in the PDF is I'm just trying to work out the probability at a specific place, and so then I have to be careful again when I look at the cases.